Good morning. My name is Jim Giacchetta. I'm one of the co-founders and CTO of Vidovation. Vidovation is a transmission, contribution, and distribution company. We help customers transport their video through the public internet, over bonded cellular, over wireless, on the network, over fiber. We basically help folks move their video content, and it's usually live. Live is a common denominator with what we do. So today we're going to talk about some of the latest developments in wireless technology. One of the biggest pain points customers have when doing live video over a wireless transmission is having as low as possible latency as possible. So I'll give you an example. If you're shooting video inside of a sports arena and you're wirelessly shooting the person singing the national anthem, and you're going up on the big screen, even if there's a frame of latency, a lot of systems have several frames of latency, but even a single frame of latency is noticeable on the big screen. And when the action on the field or the national anthem is being sung, there are systems that have low latency on the market, but these systems use very aggressive encoding. And Vidovation offers systems like this. They're at a lower price point, but I don't consider them broadcast because they're not using sophisticated compression techniques. They're actually using aggressive encoding where bits are thrown out rather aggressively, unintelligently. And there is a market for those types of products, maybe for video assist, where they're not so concerned about the quality, but they need to see the image with as little latency as possible. But what we're going to talk about today is broadcast application, broadcast quality. And the system we're going to talk about today is the only broadcast quality system with latency this low, as low as 7 milliseconds. So we're going to get into that today. Before we get started, though, let me ask you guys a question. Are any of you folks out there using a wireless system today? Is that something you're using? Just curious, kind of where the audience is at in their pursuit of technology, etc. I can show you guys the results. So it looks like it's pretty much 50-50. That's interesting. Oh no, wait, it's changing. Wait. Here, let me. I'll stop it and then I'll share it. So you guys should be able to see. I'll just read it to you. 64% of you are using some sort of a wireless system right now, and 36% of you are not. So maybe you'll learn something new today, contrarian to what you're using. We'd love to talk with you either way about your wireless needs. So let me jump in. So let's see here. Oh, there we go. So again, the biggest, the number one attribute or the number one complaint or issue is this latency. And as I said before, our partner AB On Air is the only one that does a subframe or less than a frame or 7 milliseconds, which is quite extraordinary. And any kind of application, live application, sports, cinema, drone. We're working on a couple of larger type drone projects, and they'll be flying the drone with the image, with the camera image, and if there's even the smallest amount of latency, they might crash the drone. Camera control. If the video engineer is painting the image through the system, AB On Air has extremely low latency when it comes to painting the camera. The AB On Air system is designed from the ground up to support not only video, but intercom and paint. There aren't different radios or different subsystems or a bunch of different subsystems combined to make the different functions. Some of our competitors will have a radio for the video, a radio for the intercom, a radio for the camera control. AB on Air is built from the ground up with a bidirectional radio to support everything, and has up to 50 megabits per second throughput. But I'll get to some of these features. So again, camera control, I mentioned pulling focus. So if you're controlling a camera, the iris, focusing the camera, if there's a tiny, you'll be focusing an image from a few frames ago. So there'll be this lag which will drive your director crazy. The camera won't be shaded right, or there'll always be this lag. It'll appear as if the video engineer is asleep. Why is the video engineer always falling behind? And it's not really the video engineer's fault. It's the wireless camera system. It's delays in the radio. So all RF radios, all microwave radios have some sort of modulation scheme. So what does that mean? Well, in simple terms, if we send one bit through the system at a time, like high, low, on, off, that would be a very rudimentary kind of AM type of transmission scheme, and we would be very limited in the bandwidth that we could use or the throughput that we would get. So in modulation schemes, there's techniques that will send more than one bit per symbol, or as you can see here in the slide, QPSK, quadrature phase shift keying, is actually 2 bits per symbol, or there's 4 actual states. You can see here to the right, here's a diagram of that. So it's 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So there's actually 4 states in a given word or a given symbol. You could think of it as like a data bus in a computer. A rudimentary microwave system would have a 1-bit bus. So by doing some modulation techniques, quadrature phase shift or 16 QAM, higher order modulation allows us to put more bits through. So hence we're making a wider bus. So in a given bandwidth, say we have an 8 megabits bandwidth to deal with, we can fit much more throughput in the available bandwidth. Now, in everything in life, there's trade-offs. When you use higher order modulation like QPSK or 16 QAM or even 256 QAM, you can see here there's more states. The signal, the payload is more complex. It requires more processing, so you need to have more horsepower, more computing power on both sides. But then it also becomes more sensitive to noise and interference. So in a lot of cases, it's desirable to have this modulation scheme adaptable. Now, all of our competitors have different modulation settings, from rudimentary to more complex, but you have to stop the unit, go into the settings, go into the menu, and change the modulation scheme. So if you get into kind of a dead spot in your RF footprint, on the third base side, there's kind of a dead spot. Maybe there's some interference. Maybe there's some obstruction between you and your receiver. Whatever the case may be, you'd actually have to stop your transmission, go in and change the modulation settings. Now, do you want your cameraman doing that, or the video engineer in the truck's got to deal with that? The AB on Air system adapts the modulation scheme automatically. So if the link is very good, very clean, there's no noise, there's no interference, it will use a higher order modulation scheme and hence give more bandwidth, double, triple, even quadruple the bandwidth, quadruple the throughput compared to some other systems, and then dynamically change. If you get to the fringe of your RF budget, like you're getting a little too far from the receiver, the modulation will go less complex, and the picture quality will go down. But in most cases, I think you'd rather have a slightly reduced picture quality and still have a picture than opposed to the picture all of a sudden just stopping or the transmission having a problem. So that's a key feature. Everyone does some sort of modulation scheme. It's the nature of the beast, or nature of microwave radios, it's having it be adaptive, having it be intelligence. That's the big differentiator. So some of you folks may know this already, but in addition to the encoding schemes, there's different types of modulation or transmission schemes. So orthogonal frequency division multiplexing, or OFDM or COFDM. When you put the word C, it's coded, so there's some sort of extra coding being added on top of the transmission, and typically the coding refers to forward error correction. I have a whole nother PowerPoint presentation. I have an ebook actually on our website that goes into the science behind forward error correction. But basically, the basic principle of forward error correction is if we add 20% extra forward error correction, or if we add 20% redundancy. So if we set our FEC to 20%, theoretically we could lose 20% of our packets in transmission and then automatically recover them. All systems do this, and they have, like high, low, and medium settings. You can set how much forward error correction you want, but here's the caveat. When you add forward error correction, you take away bits from the video payload. So in order to make your transmission more robust, more redundant with forward error correction, there's always, in engineering and science and physics and life, there's always a give and take. So you don't get something for free. So if we take bits away and set them aside for forward error correction, that takes away bits from the video payload. So most systems, you set the forward error correction and you leave it alone. You set it and forget it. And if you're in a very good location where the signal quality is good and you're not dropping packets, why do you need the forward error correction on constantly? Now, a video, the cameraman could go into his transmitter, or the video engineer could go into the receiver, go into the menu, stop the transmission, and lower and increase the forward error correction. Well, AB on air has the novel idea of having the forward error correction dynamic. If the system starts dropping packets, it turns the forward error correction on. If everything kind of settles out, so it's constantly turning it up and down to preserve video quality. So again, it's very intelligent how it does this. So with COFDM is very common in broadcast, and typically the bandwidth is limited to about 8 megahertz channel bandwidth, and the 5 gig band and the 7 gig bands actually allow 20 megahertz of bandwidth. So if a typical COFDM system can only utilize 8 megahertz of the channel, 17 megahertz are being wasted. Now, there's some techniques where they cascade 2 COFDM channels together to try to squeeze more into there. But I'll show on coming slides that actually, well, here at the bottom it says with the modulation techniques, with the encoding techniques, the way their OFDM radio works, you get up to 50 megabits per second throughput, which is amazing. That makes some amazing pictures, and I don't believe any of the competition can even touch that. Then you add onto that, I mentioned the forward error correction. I don't know if you folks are familiar with ARQ, or automatic re-requests of packets. So what happens is in IP transmission, you can have forward error correction, you have ARQ. ARQ, what happens is the receiver or the decoder will say, hey, I'm missing packet 101. Hey, transmitter, hey, encoder, could you resend packet 101? So there's actually a two-way communication. No other microwave system on the market that I know of is bidirectional and is able to do ARQ. In other words, there's a full duplex communication between the transmitter and the receiver. Actually, what AB on air is doing is very similar to what is done in the bonded cellular space, where transmitting through cellular and the public internet. ARQ is part of that, and there's a bidirectional directional link. So it's very, very unique what these guys at AB On Air are doing. It's very, very amazing. And so I mentioned the ARQ. Then they use a technique called variable bitrate encoding or adaptive bitrate. So I mentioned the modulation complexity will change, or the encoding complexity will change. The forward error correction will adapt. Now, if the transmitter gets far away from the receiver and the throughput should drop due to signal quality, interference, whatever the case might be, the video encoder will change its bit rate. The decoder will tell the transmitter, the receiver and the decoder will tell the transmitter, hey, you're dropping a lot of packets. I'm testing the connection, and the connection is no longer 50 megabits per second. We're now at 25. So the decoder actually tells the encoder in the transmitter to lower the bit rate to 25 megabits per second. So the encoder is going up and down in bit rate. Now our competitors, you can stop your transmission, go in and change the bit rate of your transmission, but you got to stop it. And do you want your photog doing that, or your video engineer? You're trying to get live shots in the ballpark. So if you're, with the competing systems, you're constantly tweaking. Okay, so for football, the stadium is more full, so we have more interference. So let's be more aggressive with the forward error correction. Let's lower the bit rate. You have to plan ahead of time, or there's a lot of trial and error. Everything with the AB On Air system is automatic. Everything happens. The operator, you just plug this system in, it just goes. You get the paint control, the camera control, the intercom, boom, everything comes up, it just goes. The photog doesn't even have to touch the unit. They just got to turn it on. That's all that's necessary. And all these amazing things with the ARQ, where it's re-requesting packets, it makes it even more amazing that they're able to do 7 milliseconds of latency and achieve a 50 megabit per second throughput. So again, as I mentioned, what enables all of this? This is a full duplex radio. It's built from the ground up to have full bandwidth in both directions. This is what allows the ARQ to work, the forward error correction. The receiver, the decoder, the base station is controlling everything. So it's analyzing the spectrum. There's actually a spectrum analyzer in the unit. So if the receiver determines, hey, we're on channel 3 and I'm starting to see a lot of drop packets and I'm picking up some interference, it will actually tell the receiver between pixels. There'll be no glitch. The receiver will tell the transmitter, on the next pixel, let's go to channel 1. Channel 1 is clean right now, and it will jump channels. So all this is happening automatically in the background because of the bidirectional radio. The receiver is giving the transmitter instructions. Change the modulation depth, change the bit rate. Add or remove forward error correction. ARQ kicks in. Give me those packets that I lost. And all of this happens automatically with a MIMO. It's a 2x2 type system where there's 2 in, 2 out MIMO. There's 2 antennas on the transmitter and 2 antennas on the receiver, which gives us some additional diversity and transmission resiliency as well. So what does all this gain us? So it sounds like there's a lot of complicated things going on behind the scenes. Why do we do this? Why do we bother? Well, in most cases, it increases the channel capacity or the throughput by more than 2 times. I don't think any of our competitors can come close to a 50 megabit per second throughput. I don't think that they're physically able to do that. And then I mentioned the forward error correction. It goes from 25% to 100%, constantly going up and down. Now in the competing systems, you can set the forward error correction. So if you have a very dirty connection, you could make the FEC 100%. Basically, what that means is 2 of every packet is sent for redundancy. But statistically, AB on Air has done some statistical analysis that FEC is only needed about 1% of the time. That a OFDM system is pretty reliable. So by turning forward error correction on all the time, 99% of the time, you're wasting that extra bandwidth, which could go to video. So this slide is just proving the importance of having the forward error correction be dynamic, because you rarely need it, you know, and if unfortunately, in most systems, you don't get a heads up, a time or place when the failure is going to happen. So what happens with the AB on air, the forward error correction could be set very low or maybe even off. A few packets get dropped, but the ARQ will recover them. And then if the system doesn't recover after a few packets are recovered with ARQ, it says, well, the receiver will say, I'm seeing a pattern of data loss here, so maybe we should bump up the FEC a little bit. So it brings it up, then things kind of stabilize. And then if no packets are being dropped, it may ratchet it down. But again, all this is happening in the background, all automatic. So we don't unnecessarily waste precious bandwidth that could be used for video on unnecessary forward error correction. So some of this I've already covered. I have the bad habit of jumping ahead. You know, on the first slide, I give you an overview and kind of jump ahead. But again, you know, the competition wouldn't be able to add ARQ in very easily. You know, you need a full duplex radio, and I'm not aware of any other microwave, any kind of wireless system that is doing ARQ across the microwave link. I'm not aware of anyone doing that. So that is a real differentiator for the AB on air solution. So I mentioned, you know, what are some of the variables? You know, so why, you know, so our competition uses CBR or constant bit rate. So, you know, why do we need the adaptive bit rate? So the throughput could change due to distance, which I kind of alluded to earlier. You know, if you're, you know, say you got a big football field or you're outdoors and you're at kind of the fringe of your coverage. Again, you know, if you're at the far end zone, the receiver's in the opposite end zone, I think you'd rather a picture with slightly less bit rate in the far end zone than all of a sudden it dropping out. Our competitor systems, you kind of have like this cliff effect where it's working, boom, then all of a sudden nothing, because the channel bandwidth will. So say you have your radio set at 6 megabits per second. The second the pipe dips below 6 megs, boom, it crashes. You lose the connection. Whereas this will just DAP, the bit rate will go down. It'll gradually get a little bit softer. Now, granted, you know, no wireless system is going to work everywhere every time. If you walk into a lead-lined or a steel-lined room or a Faraday cage, nothing's going to get through. But so distance is a factor. You know, these systems are mounted on cameras, so the cameraman moving around, you know, he hits that weird dead spot. External interferences. Any of you guys, any of you people out there that have worked with wireless know that, you know, there's these weird anomalies where interference comes and goes at certain times. Someone nearby is turning on a radio that interferes with your radio. And then there's changes in the medium, you know, trees, rain, walls, obstructions, etc. Let me ask you guys another question. I probably should have asked you this earlier on, but you know, I keep mentioning this latency thing. You know, having low latency. I'd just be curious if low latency is important to you guys. You know, maybe some of you guys don't care. You know, that seems to be one of the first differentiators of the AB on air. So that's interesting. So about 75% of you say that low latency is important. I say, oh, now it's changing a little bit. I'd say, you know, people where it's not so important, maybe you're not going live, so it's not as big of a deal. Oh, look at that. Now it's settled out at about 50-50. So let me share that with you. Yeah, so it looks like 50-50 is kind of the consensus on that. Very good. Let me get rid of that there. So the AB on air solution. So typically the AB on air, some of our competitors will recommend radios on the 2 gig license band or the 7 gig band, and the AB on air system has really thrived on the 5 gig band. We do have a 7. We don't have a 2 gig solution, but we do have a 7 gig solution. But then you need a license, and there's such volatility with the FCC granting people's licenses, taking them away. We think it's safer, more scalable to use the 5 gig band, and some people are afraid of the 5 gig band, and for due reason. You know, they've had problems with it. I have a little bit of a cold. I apologize. I'm taking some cough drops here. But on the 5 gig band, the AB on air system can grab either a 20 meg channel space or a 40 meg channel space, and with that can actually get 50 megabits per second throughput. And like I said earlier, no one can really touch that. And as I said earlier, the algorithm adapts. It's constantly adjusting, changing the bit rate, and excuse me, folks. You know, again, why do we go to all this effort? So when comparing this system to some of these other low latency systems, some of these lower cost low latency systems, the result is the signal to noise ratio. You know, the systems that are aggressively encoding the video, kind of throwing out the least significant bits kind of unintelligently or less intelligently than a true MPEG encoder. The end result is signal to noise ratio, and usually the rule of thumb is to have 58 dB signal to noise ratio to be broadcast or better. The AB on air is 59 dB, and if you were to do a noise measurement, you know, an AB test, the noise level coming in versus the noise level coming out on some of these other systems, you'd find the noise level is not acceptable. Excuse me, folks. I'm sorry if I blasted your ears out. So you know, so the result of all of this is better signal to noise. Hence, why we call this a real broadcast product instead of what we would consider a professional grade product. So again, you know, I don't think any of you guys want your photogs messing, you know, with complicated systems. You know, we find this with our bonded cellular product. Photog, the photog just wants to turn it on. Maybe they got to hit a transmit button, and that's it. It just needs to work. Same thing with the AB on air. All the operator has to do is turn it on, slap a battery on it, turn it on, and it's ready to go. There's no setup, no decisions that have to be made. Everything is just automatic. So no special training. You know, do you want your photog having to read the manual, how to go through the menu to change the modulation, change the bit rate, change the forward error correction? AB on air is all automatic. So do any of you guys run into situations where you wish you could have coverage in multiple zones? So what do I mean by that? You know, coverage in the football arena, coverage in the basketball arena with the same system. Or another common scenario is have some antennas inside the bowl of the arena, then maybe you want to catch the team as they come out of the tunnel. But the tunnel is outside the field of view of the receiver. So AB on air has, it looks like all you guys, yes, that's desirable. That's good to hear. Let me share that with you. So 100% of you guys said yes. So you know, maybe you want to get shots in the tunnel. You want to get shots in the dressing room as the team comes out. A shot in the press area. Our competition has several ways to do this. You either need multiple receivers, and then you'd home run the SDI video of those receivers back to the truck or the control room. Or another method is called a distributed antenna system, where you move the raw RF around and you have bulky RF cables. There's techniques where they down convert the RF to an intermediary frequency, a lower frequency, so there's less loss when it goes over the cable. But then again, there's distance limitations. These cables are bulky. There are techniques that the RF signal is actually a very wideband analog signal, a very high frequency wideband analog signal. There's very expensive fiber optic equipment to extend this broadband RF over fiber, but this is very expensive. So again, AB on Air kind of takes a playbook from cellular. They have what they call fiber coverage extenders, and they operate very much like cellular sites. So you can have up to 256 of these FCEs, as they call them, connected to a single receiver. You could have, if you have a very large football field, maybe you have 2 antennas, or like I said, 1 in the field, 1 in the tunnel, 1 in the dressing room, 1 in the press room. Then you have 1 over the basketball arena nearby. So the photon just lights up wherever he needs to go. You know, particularly in college campuses, you might have multiple venues in close proximity on the same campus. But you know, I can think of take Toronto for an example. The Leafs, the Blue Jays, the stadiums are all pretty close to each other. So you could have each venue lit up. You might be the same production company running multiple facilities near each other, or they could be 20 kilometers away, because this operates over a dark fiber. So the same production company is doing a Rangers game at Madison Square Garden, and then they're doing Nets games at the arena in Boston, not in Boston, in Brooklyn, and that's all connected via dark fiber. The photog just shows up and lights up. Boom, he's back to master control. So it's all seamless over dark fiber, very much like cellular. And the transmitter will talk to the base station or the FCE it's closest to. So if you're in this football field and you kind of get far away from a given receive node, but you're closer to the receiver in the tunnel, like you're starting to enter the tunnel, the unit will jump to that other receiver, the closer receiver, or the receiver with a better signal, between packets. There's no loss, there's no glitching. So this multi-zone coverage feature is extremely powerful, and customers are loving this. So you can almost limitless coverage. Up to 256 of these can be connected together. It's a small little box. Some of the boxes are simplex, meaning it's more of a star configuration. You can see the one here in the PowerPoint. It has 2 fiber ports on it. So one could be going to the base station and loop out, so you could daisy chain them together. Or AB on Air makes a fiber hub, so you could do more of a star or a hub and spoke type configuration, or a daisy chain configuration. And the video, the camera control, the tally, the intercom is all passed through these multiple nodes, and it jumps between nodes without a single hiccup, without a single glitch. So here's another way of looking at it. You know, so you got the basketball arena, the football field. You have multiples of these FCE receivers, all home run to the base station. If you have more of these, you can daisy chain them together, or there's a hub where you could bring 256 of them excuse me, into the hub, and then bring them into the base station that way. So it's all seamless. So here's a topology of the old way of doing it. So you have a receiver at each of your venues, which is expensive. You need a full base station at each venue. Then they might use a fiber optic infrastructure, SDI infrastructure, to bring it back. Then you need a switcher to figure out which one of the venues you want to receive from. As I mentioned before, that they might push the raw analog wideband RF over fiber, which adds to which is extremely expensive. These fiber extenders are not very expensive. So these FCEs, these fiber coverage extenders, you see how simple it is? You home run them. It's a a duplex, a pair of dark fibers connecting these. And with 256, we're talking to broadcasters where, say like Washington D.C., they want to light up on the mall outside of Washington D.C. In front of the Capitol, and then they want to light up in other areas, inside the Capitol. Imagine D.C. bureau, they're jumping around, the press conferences, different areas, different buildings. There could be these FCEs all over town, home running back to their master control, and their photog can literally light up anywhere in town and go live as long as he's within. These units have about a 2-mile range, so as long as he's within a 2-mile line of sight of one of these FCE receive sites, he's ready to go. He can broadcast live from anywhere. Someone was asking, do I need to have a switcher on the fiber? Nope, it's just a hub. It'll automatically, the receiver is actually looking at receive packets from all the FCEs, but the transmitter will actually jump to the FCE it's closest to, or the FCE it's getting a signal from. So let's just say, packet number 1 comes from FCE number 1, then the camera moves, the next packet, the receiver magically puts that all together. So there's no fiber optic switching. No user intervention of any kind is required. It just magically works. That was a good question, Dan. I think that answered your question. Let me keep going here. Yeah, keep the questions up. I'll scan them at the end when I'm done. I'll go back to them and answer them. So systems out there either don't have paint control or are missing something. It's rare that you find a complete system. Even the systems that are complete, if you dig under the hood, it's actually systems from multiple vendors that are packaged together. The video will be on one rudimentary simplex radio. The camera control will be on another band from another vendor. They'll have the two systems don't really talk to each other. There's no redundancy across these different systems. And then some of them will have an intercom from yet a third vendor. AB on Air was designed from the ground up, having this bidirectional radio to do intercom, to do IFB. There's interfaces on the receiver for 4-wire or 2-wire. It'll integrate with, we haven't found an intercom system it doesn't integrate with. The paint and camera control, we're adding new cameras every day. We support Sony, Panasonic, Ikegami, Grass Valley, and Hitachi. We're working with some of the Blackmagic cameras now. Excuse me. So it's a very robust system. So again, to summarize, the big takeaway is getting that low latency, but again, not sacrificing video quality. This is a true broadcast system with subframe, less than a frame latency, 7 milliseconds. True broadcast quality, up to 50 megabits per second. But remember, that's adaptive. Your modulation scheme, your adaptive bit rate encoding, the modulation complexity is going to change. How many bits we get through per symbol. The bit rate is going to change. Forward error correction is going to change. So the unit is slow to fail. You don't have that cliff effect where it's working and then bam, then nothing. And then integrating these advanced features, intercom, camera control, And then finally, but not last but not least, is this multi-zone coverage. Customers are blown away by this. And here's the thing: out of the broadcast solutions that are out there, AB on air is the most affordable. So believe it or not, it's the most advanced in technology, but it is also the most affordable. So I think the reason for that is because it was designed from the ground up to have all these features. So it's not a bunch of different boards from different vendors kludged together. So I think it's a more streamlined design, hence the lower cost. It was designed properly in the first place. It's not a lot of things band-aided on there. So there's a couple of things. AB on Air has some surprise announcements for NAB. Some of them I can't talk about yet, but I talked to the CEO yesterday and I said, you got to give me something for the webinar to get people excited about NAB. So they've taken their technology. So the standard unit is the AB512. That's the flagship unit, and that's a typical package is usually a transmitter, a V-lock or Anton Bauer mount, a base station, a 1RU base station, and one of the fiber coverage extenders. Usually the base station is in your master control or in your truck, and then the fiber coverage extenders out in the stadium. So a typical setup for a truck, for each of the cameras, each of the wireless cameras in your truck, you would have a transmitter, a 1RU base station, and an FCE. If you have 3 cameras, you need a set of 3. There are systems coming that have more capacity, but I don't want to spoil things for NAB. But one thing I can say is they have a long-range point-to-point system that will be coming out. I haven't seen it yet, but I imagine it has directional antennas. It will maintain the 7 millisecond latency. It'll go up to 10 miles or 16 kilometers with the intercom, IFB, camera control, and paint, just like the flagship systems. But, let's just say some applications we've done where the actual studio in the stadium, the studio for the stadium is not actually in the stadium. We did one project with Carolina Panthers where we did a wireless link a mile or so from the stadium to an ancillary building where the production studio resided. So there's always unique situations where the video needs to go longer distances. Excuse me. So if you want to, there's some preliminary information about NAB, Vidovation, and some of our partners, AB on Air, Avi West, Antelope Cameras, our IPTV systems. If you go to vidovation.com/NAB19, there'll be updates. So visit there. You're welcome to visit there now, but check back often to see if there's any new news. A little bit more information about Vidovation. At the top of the slide, I said we're a video transmission, contribution, distribution company. Our tagline: moving video forward. We help our customers move video. Most of what we do tends to be live. Live sports. We're doing live reality shows like Live PD. We did the Riders Cup with Turner Sports, moving 16 ISO cameras from Paris to Atlanta, doing a REMI at-home production. We're very good at doing very perfect gen lock and lip sync of multiple cameras to be able to do a REMI or an at-home production. And then we're a consulting company. We have a wide variety of solutions. Some manufacturers, they have a finite product set, so they'll try to fit one of their square pegs into your round hole. Vidovation, we find the right solution to solve your problems, your pains. We'll even create a product to solve your pain. The NHL had a problem with in-net officiating, so we designed and developed a custom in-net wireless camera system. So maybe you have a project similar to that. So that's kind of the summary. Let me go on. I'm going to leave it on this slide so you guys can see the link for NAB. Any of you guys have any other questions? Yeah, so Dan, you had asked, how is this different than a distributed antenna system? Hopefully I answered that. Yeah, I like to tell customers, can you do this? Can you do that? I mean, anything, given enough time and enough money, just about anything can be done. We threw Kennedy threw enough money at the space program to put a man on the moon. Back in the 60s, people thought that might be impossible to do. But, given the time, the money, and the manpower, pretty much anything can be done. There's systems out there that are working, but, they're more complex. They're more expensive. You need these bulky cables. We'll go into a sports venue, and they have available dark fiber at every camera position throughout the facility, and those fibers go down to the truck bay. So it's actually very, very easy to put an AB on air system into a fully operational stadium. We just find an ideal spot to put the fiber coverage extender, that receiving node. Just need a pair of dark fiber and power, obviously, and then connectivity from that point to the truck bay, and then inside the truck is the 1RU receiver. Look at. Hope you guys downloaded some of the. That have a handout. Our marketing team will send a follow-up after in the coming days. You'll get an email about the summarizing what we talked about. We'll give you a copy of the PowerPoint, and then also we're recording this, so there'll be a video to go with this. Again, I apologize, guys, if I blew any of your ears out with my cough, but hopefully this was informative. If you guys have any other questions, give me a shout, and I can answer the questions offline. So thank you very much. Oh, let me leave up my contact info. So if you want to reach me, jimj@vidovation.com. That's my email. That's the best way to reach me. You can see here I'm on social media, or call the team. Talk to our VP of Sales, Rick Anderson, or anyone on the team. We'd love to help you guys. And thank you so much for tuning in today, and have a great weekend. Thank you so much.